Hello, everyone. I'm Hawkin Cha. I'm a PhD student at UW-Madison, and I'm going to present our paper, Building Cache, an adaptive hybrid index for in-memory time series databases. The time series database has recently gained huge attention with the development of many IoT devices. There are largely two requirements for the time series database. First is high-speed data ingestion capabilities. IoT devices generate massive amounts of data in real time so that the speed of data processing should match the speed of data generation. And the second is efficient data analytics. IoT data is an essential source for machine learning and data analysis so that the database should provide efficient analytical processing capabilities. A lot of time series databases have been trying to accommodate these requirements by changing their database internals. However, indexes have not received such attention. Conventional indexes are still widely used in time series databases. So we did an experiment to see if today's main memory index designs are actually suitable for the time series workload. And this figure shows the throughput of the indexes with an increasing number of threads under monotonic insertion. To our surprise, none of them scales except for a hash index. A hash index is not affected by the pattern of keys because hashing converts monotonic keys into random numbers. But hash index has limited functionalities. It does not support range scans, which makes tree indexes crucial for database systems. So this experiment demonstrates that existing tree indexes cannot support fast data ingestion of the time series workload. It is a big problem because not only the insertions will be slow, but these insertions will also slow down the other index operations due to the conflicts. The main reason existing tree indexes cannot scale is that most insertions are serialized due to the pattern of monotonic keys. It is the characteristics of time series workloads that time-stamped keys monotonically increase over time. This means that new keys will be larger than existing keys inside the index. Therefore, all the threads will try to insert in rightmost node at the same time, and this causes the serialization of index operations. Also, this behavior stresses a single memory location, which causes high cache coherence latency among all the access cores. So we have identified that existing tree indexes have a fundamental limitation under the time series workloads. Now we need a new index design that can keep up with this high speed of data generation. But at the same time, we want to keep the strength of tree designs in analytical queries. Therefore, we present Building Cache that integrates a hash index into a tree index. Previously, we have seen that a hash index is not affected by the characteristics of P patterns because a hash function converts monotonic keys into random numbers. So Building Cache can leverage the strength of both tree and hash indexes of high performance in range scans and heavy insertions. Building Cache consists of two different structures. We keep B+3 nodes for internal nodes and replace the leaf nodes with hash nodes so that the high contention in rightmost nodes can be evenly distributed to different hash buckets within a hash node. However, this design introduces new challenges. First, splitting a hash node becomes the new scalability bottleneck. As keys are not sorted within the hash node, we need to collect all the keys and sort them to find the median to update its parent nodes. And after that, we need to migrate about half of the key value records to a new hash node, which causes a huge amount of write traffic, considering that its size is much larger than that of conventional B+3 nodes. The second challenge is range scan is not efficient. Again, due to the unsorted keys, scanning a hash node causes extra sorting overhead. So from the next part of the talk, I will discuss the techniques we use to resolve these challenges in Building Cache. But let's start with the first one. We need to find the median key when splitting a hash node. but it's expensive to read all the buckets just to find one single median key. So we minimize the overhead with approximation. Instead of sorting all the keys to find the precise median, we only visit a small number of buckets and find an approximate median within the sampled subset of keys. After finding the median, we need to migrate about half of the records to a new hash node. And this causes a huge amount of write traffic inside the critical section, which is the split operation. And therefore, we delay such migrations with lazy splits. It does not migrate the key value records inside a split operation, but delegates the responsibility to subsequent thread accesses after the split. A hash node consists of multiple hash buckets, and each hash bucket has a linked state variable, which denotes its stableness. This variable lets subsequent threads know that currently accessed bucket is stable or not. If it is stable, it means that all key values in this bucket are in the correct position. If it is not stable, the state will be either link left or link right. Link left means that some key values are located in the left sibling node, and link right means that some key values in this hash bucket belong to its right sibling node. So I'll go through some examples to show you how this works. Suppose we have a hash node and we are trying to insert key 15. Since the bucket 0 is full, we need to split this hash node. We first find the median using the approximation technique. We will make the sample subset of keys with 3 keys in this example. Then the median should be 12. Now we allocate a new hash node and mark all its states to link left. Then we also update the bucket states in the original node to link right. The link states in the same indexed buckets create a pairwise logical link between the two adjacent nodes. Then we try to insert 15 to the new node since it is larger than the median 12. But we always need to check its link state first. It's not stable, it's link left. So we need to stabilize it by migrating some key values from its left sibling node. We move 33 to the new node and then update the states of the 2 buckets to stable. Then now we can insert 15 in the new node. Finally, we create a parent node with the median we found in the first phase. And this completes the split operation. We leave the rest of the buckets unstable and let subsequent threads stabilize them later. Let's see another example where a subsequent thread stabilizes a bucket after the split. A thread is trying to insert key 8. It will access bucket 2 in the left hash node. It first checks the bucket state. It's not stable, which means that some key values need to be migrated to its right sibling node. Since both keys are larger than 12, which is the separator key of the node, it migrates keys 20 and 25 to its right sibling node. Then it updates the states of the 2 buckets to stable, and now it can insert key 8 into the bucket 2 in the left hash node. So this lazy split, this breaks down a node level critical section into much smaller bucket level critical sections. It leverages high parallelism by letting other threads help complete the expensive key value migrations outside the split operation. This figure shows the architecture of B-Link hash. Some buckets are stable and some are not, but they are always logically connected to each other in a pairwise manner. Next, we move on to the second challenge, inefficient range scans. Since the keys in the hash node are not sorted, we need to visit all the buckets and sort keys to get the correct result, which is not very efficient. We use structural adaptation technique to overcome this inefficiency. Structural adaptation converts a hash node into B+3 nodes upon a scan access to leverage the strength of sorted key scans. But we always keep the rightmost leaf node as a hash node because considering the characteristics of time series workload, it is very likely that new insertion keys will be larger than the existing keys inside the index, while incoming queries will access somewhere in the middle of the tree. Therefore, we keep the rightmost leaf node as a hash node for future scalable insertion performance. But we convert the other leaf nodes to B+3 nodes for scan efficiency. Let's see an example of scanning the leaf node L2. But before doing the conversion, we need to make sure that all the buckets are stable. The second bucket in L2 is not stable, it's linked left. So we traverse to its left sibling node L1, and then migrate keys 25 and 33 to L2. Then update the bucket states to stable. Now we can convert it, and we allocate B+3 nodes with the sorted keys and update its sibling pointers and update its parent node to point to the new B+3 nodes. Structure adaptation helps building cache to dynamically adapt to workload variations. After running for a sufficiently long time, a building cache will converge to a building tree structure. This figure shows the architecture of building cache after running some workloads. Many of hash leaf nodes have been converted to B+3 nodes, and some of them stay as hash nodes. And rightmost leaf node is always a hash node for future insertion. Now we evaluate building cache against today's representative main memory index designs, including ART, HOT, mass-tree, OpenBW tree, and in-memory version of building tree. All the experiments were conducted on a machine that has two Intel Xeon Go CPUs with 512 gigabytes of DRAM. We evaluate the indexes under two different workloads. We use time series workloads to test the scalability under monotonic keys, and we also use YCSB workload to demonstrate that building cache is not limited only to supporting the time series workloads, but is also expanding its functionalities to various workloads. The figure shows the throughput of the indexes under time series workloads with increasing number of threads. On the leftmost figure, building cache is the only index that scales under the monotonic insertion. It efficiently distributes the high contention in rightmost nodes to different hash buckets, while the other indexes suffer from serialized insertions. Building cache also shows better performance in read workload because the large size of its hash node reduces the height of the overall tree structure. In scan workload, building cache shows comparable performance to building tree with the structure adaptation that dynamically converts hash nodes into B+3 nodes. In mixed workload, which consists of a mixture of all the operations, building cache shows scaling performance while the others fail to scale again. This means that only 50% of monotonic insertion is large enough to destroy the performance of existing indexes. And finally, we evaluate building cache under YCSB workload with email keys. Building cache outperforms the other tree indexes in most workloads, except for workload E, which is scan intensive. But it still shows comparable performance to building tree with the structure adaptation optimization. In conclusion, we have identified the fundamental limitation of today's index designs under time series workloads. We present building cache that resolves the problem by integrating a hash index into a tree index. We also propose three optimization techniques: median approximation, lazy split, and structure adaptation to leverage the strength of both B+3 and hash indexes. And finally, our evaluation study shows that building cache is superior to today's index designs in time series workloads and even in OLTP workloads. Thank you for listening. This is the end of my talk.